Okay, today in Honors Chemistry, we're going to talk about molecular geometry and do quite a few drawings. My drawings probably are not the best in the world, so there are a lot of places on the internet you can go to pull up animations of different types of molecules. And one website in particular is pretty good. It's called chemibear.com, and then go to the animated molecules section, and then it shows these molecules with some movement with them. So it's a little bit more interesting to look at. So once you have correctly drawn the Lewis structure for a molecule, you can determine the geometry or shape of it by using something called the VSEPR model. VSEPR is VSEPR, which stands for valence, shell, electron pair repulsion. And it basically states that valence electron pairs surrounding an atom will repel one another so that the orbitals containing those electrons are oriented as far apart as possible. The repulsion among electron pairs in a molecule results in the atoms existing at fixed angles to each other. The angle formed by any two terminal atoms in the central atom is called the bond angle. So each of these geometries will have a certain bond angle that goes with them. Okay, so we're going to start out with molecules that have no lone pairs around the central atom. So our first example is an AB2 molecule. All AB2 molecules will have a linear geometry and 180 bond degree angle. The A stands for the central atom. The B's are the atoms that are bonded to the central atom. So this is just saying there are two atoms bonded to our central atom. This occurs when there are only two pair of electrons shared off the central atom. So we're talking about these elements in 2A because they have two valence electrons, usually just going to be Be and Mg, and depending on who you put them with over here. These will show something called sp hybridization. So I'm going to show you where hybridization comes from in a second. Once again, my explanation is not very good, and so make sure you read about that in your textbook or on a website someplace. Okay, so we're going to do BeCl2. So Be, beryllium, is in 2A, so it only has two valence electrons, so it will not follow the octet rule. So when we draw it, we have BeCl2. Be has two valence electrons. Chlorine has 7, but we have 2, so that's 14. So we have 16 electrons to work with. So we're going to do the Lewis structure, okay? So Be is your central atom. You're going to bond to chlorine. You're going to bond to chlorine. Remember, this is a single bond, so it represents 2 electrons. So 2 and 2 is 4. So minus 4 electrons used. So that gives us 12 electrons left over. We're always going to fill our terminal atoms first. So this is 6 pairs. So 1 pair, 2 pair, 3, 4, 5, 6. So we have used 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons available. This chlorine has 8. This chlorine has 8. This beryllium has 4. Okay, so let me explain to you this hybridization a little bit more. Okay, so beryllium, if you look at beryllium's electron configuration, it's 1s2, 2s2. Okay, since its s sublevel is full, holding 2, what happens is, so if you do this for your s, you have 2 electrons here. Your next would be your 2p, so this is your 2s. This is your 2p. We're going to take one of these electrons and move it over to the s. So now we have a position for an electron to be shared at one of the s's and one of the p's. So that's where the sp comes from. The way I do it, so I don't have to do this every time, is I just look at the number of things on the central atom, even if it happens to be a lone pair, and I count them all as something. And so I say this one goes into the s and this one goes into the p. So it has sp hybridization. And so here is a better drawing that just shows that you're going to have a bond angle of 180. So from here to here is your 180. Okay. And if you have a molecule that it contains just 2 atoms, it is also considered linear. So for instance, Cl2, we could do F2, O2, HCl. Okay, our next type of molecule is called an AB3. So remember, this means there are 3 atoms bonded to our central. These molecules will have a trigonal planar geometry and a 120 bond angle between the terminal atoms. it will show sp2 hybridization. So we're going to draw AlCl3. So I'll move this up where you can see it a little bit better. Aluminum gives us 3 electrons. Chlorine gives us 7, but we have 3, so that is 21. So we have 24 electrons to work with. So we have Al, Cl, Cl, Cl. We have 3 single bonds, 2, 4, 6, minus 6 electrons. Leaves us 18 electrons, or 9 pair. 1, 2, 3, 4, 5, 6, 7, 8, 9. Go back and count to make sure you did not use more electrons than you were allotted. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. This chlorine has 8, 8, 8. Aluminum has 6. Aluminum only has 3 valence electrons, so it also does not fit the octet rule. Okay, so your bond angle from here to here, here to here, here to here would be 120. If you draw it just right, I did not. Okay, you have 3 things around your atom, so we're going to go spp. So it's going to have sp2 hybridization. So here is a drawing from a textbook. Okay, our next molecule is an AB4. AB4 molecules will have tetrahedral geometry. Tetra means 4, so that makes it easy to remember the geometry. So there's going to be 4 atoms bonded, and your bond angles are 109.5. Your central atom, once again, has 4 atoms bonded to it. It will show sp3 hybridization since it has 4 things around it. 1 will go in the S, and the other 3 will go into each of the P's. Okay, so we are going to draw CH4. Methane, so CH4. Carbon gives you 4 valence electrons. Each hydrogen is 1, but you have 4, so we have 8 to work with. So we have carbon, hydrogen, 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 hydrogen. We've just used 2, 4, 6, 8. That's all we had. And so carbon has 8 available, and hydrogen has 2. Now, anybody, if anybody in 4A is your central atom, carbon, silicon, germanium, they're going to always show the same geometry. The same for aluminum. Boron, they have the same molecular geometry. The same for Be and Mg. Okay, so anybody in a family would show the same kind of geometry as what we're talking about. Okay, so here's the thing. If you think of this as laying flat, you're going to go, oh, we have 360, and we're going to divide it by 4. You can get 90-degree bond angles. That is not true. So what we do is, this is going to kind of look like, it's going to, I don't know if you've ever played with jacks. You know how jack doesn't sit flat, lays flat, it just kind of stands up. That's how this molecule looks. So I'm going to put some wedges in here, and I probably are not drawing them in the correct sequence, so you're just going to have to trust me on this, or go find a picture. So think of these 2 H's as kind of going behind the board and our paper, and this one coming out, so it's not going to lay flat. So your bond angles, so between this, any 2 hydrogens would be 109.5, okay? So you have 109.5 degree bond angle, sp3 hybridization, SPPP. So here is a drawing that shows you, so you think of it as not, it doesn't lay flat, it kind of stands up. Okay, our next example is an AB5 molecule. AB5 will have trigonal bipyramidal. It's easy, this one's easy to remember also. If you have 5 atoms bonded, tri means 3, bi means 2, so that gives you 5 atoms around it. You're going to have 2 sets of bond angles, 90 and 120. Once again, A is your central atom, B is your bonded, so you have 5 atoms bonded. Okay, and it's going to show sp3d hybridization, because remember, you only have 3 P's. So one of them go in the S, 3 more will go into each of your P's, and then you're going to go into one of your D's. Okay, so we're going to draw PCl5 as our example. Phosphorus is in 5A, so it gives you 5 electrons. Each chlorine gives you 7, and there are 5 of them, so that's 35. So we have 40 electrons to work with. So we have phosphorus, chlorine, 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 chlorine. Whoops, chlorine. Okay, so we just used 10 electrons. That leaves us 30 or 15 pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this chlorine has 8, this chlorine has 8, this chlorine has 8, and this chlorine has 8, and this chlorine has 8. Phosphorus has 2, 4, 6, 8, 10. So remember, you can have an expanded octet when you're in period 3 or down, and phosphorus is in 3. So it's got a 3d orbital, and so available, and so phosphorus will have an expanded octet. Okay. Hybridization, an S, a P, a P, a P, and then a D. Okay, here is a drawing that shows you a better visual than what I have on the paper. Okay, next up we have AB6. AB6 shows octahedral geometry and bond angle of 90. So that this 6 once again means you have 6 atoms bonded to your central atom. It will have sp3d2 hybridization. Okay, so we're going to draw SF6. Sulfur is in 6A, so it gives you 6 valence electrons. Each fluorine gives you 7. 7 times 6 is 42. So we have 48 electrons to work with. So we have sulfur, fluorine, 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 fluorine. We've just used 12 electrons. That leaves 36 or 18 pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Each of our fluorines has 8. Our sulfur in this instance has 2, 4, 6, 8, 10, 12. So once again, it has an expanded octet. You have an SPPPDD. So it has sp3d2 hybridization. Between any two of these terminal atoms, there should be 90 degrees. So you're going to have some wedges. So here's a wedge, here's a wedge. Okay, so be sure and stick a couple of wedges in to help you visualize that. Okay, also you're going to have molecules, some molecules that you draw that have multiple bonds. When you're doing geometry, even though it has a multiple bond, it's going to be treated like a single bond for doing geometry. Okay, now we're going to come across something that's a little bit different in that we're going to talk about molecules that have lone pairs around the central atom. So this is where drawing the correct Lewis structure is really important. So lone pairs are also important in predicting shapes of molecules. That is because lone pairs will strongly repel the bonding pairs, pushing them together closer than you might expect. So our first molecule, our generic formula is AB3E. Once again, A is your central atom, B are your bonded atoms, E represents your lone pair of electrons on your central atom. So, so you're going to have 3 atoms bonded to A and then 1 lone pair. All AB3E molecules will have a trigonal pyramidal geometry with a bond angle of 107. Some books will say less than 109.5, but we're going to go with 107. Okay, so hybridization will be sp3. So you're going to think of your lone pair as a thing, and so you have 4 things around it, so that's why it's sp3. Okay, so we are going to draw NH3, ammonia. Nitrogen is in 5A. It's going to give you 5 valence electrons. You have 3 hydrogens. They each give you 1, so that gives us 8 total. So when we draw it, we have nitrogen, hydrogen, hydrogen, hydrogen. We just use 6 electrons. That leaves 1 pair. Remember, you cannot give hydrogen anymore, and so the only place that electron can go is on nitrogen. So you can either draw a line, or you could have alternatively put just 2 dots. Okay. Though that lone pair pushes these hydrogens together, so it's going to make a pyramid, and so it's going to look something like that with a wedge in it. Okay, so here is the drawing. So this is your lone pair. Here are your 3 atoms. This is showing 109.5, but I go with the 107. Okay, next up is AB2E2. So this indicates that we're going to have 2 atoms bonded to our central atom, and we're going to have 2 lone pairs on our central atom. AB2E2 molecules will have a bent geometry. Some people will say V-shaped. Your bond angle is 105. Your hybridization is going to be sp3. Since you've got 2 atoms and 2 lone pairs, that gives you 4 things around it. Okay, we're going to draw water. So water is H2O. You have 2 for your hydrogens and 6 for your oxygen. That gives you 8 electrons total. So we're going to have oxygen, hydrogen, hydrogen. We just use 4 electrons. That leaves us 4 left over, or 2 pair. So we're going to put 2 pair on oxygen. Okay, so you could just draw straight lines. These lone pairs push these hydrogens closer together. Okay, so a lot of kids will draw it like this, and they'll put their lone pairs, but then they don't remember that these lone pairs are pushing these hydrogens closer together, and they'll call it linear, so be real careful. Oxygen, anybody in oxygen's family, oxygen, sulfur, selenium, if they're your central atom, they're going to do the same thing. They're going to have a bent geometry. Okay, next we have AB3E2, which have a T-shaped geometry and a bond angle less than 90. So we're going to have 3 atoms bonded and 2 lone pairs. We're going to draw ClF3. It's going to look kind of like this, and my drawing probably will look nothing like that, okay? So we have ClF3. Chlorine is our central atom. It has 7 valence electrons, and we have 3 fluorines, each with 7, so that's 21. So we have 28 electrons to work with. Okay, so we have, let's read this over here. So we have chlorine, and now we have, we're going to put a fluorine, a fluorine, a fluorine, 2, 4, 6. That leaves us 22 or 11 pair, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're going to have 2 lone pair on our central atom. Okay. And so that will give you T-shaped geometry, and there should have 90-degree bond angle between your terminal atoms. Okay. Next up is an AB4E molecule. We'll show a seesaw geometry. Bond angle, 2 sets of bond angles, a little less than 90 and a little less than 120. You're going to have 4 atoms bonded to your central and 1 lone pair. Since you've got 5 things around it, it's also going to be sp3d hybridization. And we're going to draw SF4, and here's what it looks like. And my drawing, once again, will probably not look near like that. Okay. So sulfur is in 6A. It gives you 6 valence electrons. Your fluorines give you 7. You have 4, so that is 28. So that is 34 electrons available. So we're going to have sulfur, and we're going to have a fluorine, a fluorine, a fluorine, a fluorine. We just used 2, 4, 6, 8. Gives us 26 or 13 pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That leaves us 1 lone pair left over, and we're going to put it on our central atom. Okay. Okay, next up is an AB5E molecule. AB5E molecules will have square pyramidal geometry at bond angles of less than 90. So this tells us we have 5 atoms bonded to our central and 1 lone pair. Since you've got 6 things around it, it will be sp3d2. So 1 in the S, 3 in the P's, and 2 in the D's. Okay, we're going to draw BRF5. So this is what it should look like. So we have BRF5. Bromine is in 7A, so it's going to give you 7 valence electrons. Fluorine is also 7A, and you have 5, so that is 35. So we have 42 electrons. So we're going to draw bromine. We're going to put a fluorine, a fluorine, a fluorine, a fluorine, a fluorine. We're going to put some wedges here, okay? And then we've used 2, 4, 6, 8, 10. That leaves us 32 or 16 pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we have one lone pair, and we're going to stick it on our bromine, okay? So you have 6 things around your central atom, so S, P, 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 D, D. Okay, last up is an AB4E2 molecule. They will show square planar geometry and bond angles of 90. So this tells us we have 4 atoms bonded to our central atom and 2 lone pairs. Hybridization, we have 6 things around it. So 1 will go in the S, 3 in the P's, and 2 in the D's. Okay, and we're going to draw ICL, ICL4 minus. I looked at that wrong for a second. ICL4 and a minus charge. So iodine is in 7A, so it gives you 7 electrons. You have 4 chlorines, so 4 times 7 is 28. So that gives us 35, but we have an extra electron since it's a poly. So that gives us 36 electrons. And it should look something like this, okay? So I'm going to try and draw as close to that as I can. So we have I, we have a chlorine, 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 chlorine. So we just use 2, 4, 6, 8. That leaves us 24 or 12 pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 30, 32. So we have 4 electrons left over, and so we're going to put them on our iodine, okay? And we should have a couple of wedges in here, okay? All right, and so that is going to be square planar. Okay, so that takes care of it in this section. There are other geometries that we have not done, and so you're welcome to read further on about this. Thank you.